Welcome to clickmyproject.com. Let me discuss about the project low complexity ICI suppression methods utilizing cyclic prefix for OFDM systems in high mobility fading channels. Let me discuss about the abstract of the project. Orthogonal frequency division multiplexing is a modulation technique. It is orthogonal frequency division multiplexing is known to be resistant to frequency selective fading environments. This OFDM linearly operated on intersymbol interference free part of cyclic prefix. However, then employed over doubly selective channels with high Doppler rapid time variations destroy the subcarrier orthogonality and introduce intercarrier interference. There is a need to suppress the intercarrier interference. This paper achieves to suppress the power in an ICI effect. Here derive optimum combining weights for ICI suppression and produced 3 sets of optimal solution to this problem. One method is derived optimum combining weights which minimize the ICI power after segment combining. However, this method not considered noise environment, so that proposed method were obtained optimum combining weights that minimize the ICI plus noise power simultaneously. This second method considered only non-polluted region alone, even polluted region also having signal information. So there is need to consider polluted region also. Finally, method 3 proposed that employs entire cyclic prefix which includes both ICI polluted region and ICI free region. This method also produces optimum combining weights which used to minimize the average interference plus noise power. First two is used when delay spread is small, so that polluted region much small. Method 3 much outperformed when delay spread is large with CP length is larger. In this proposed method, narrow band flat subchannels has been computed with slanted transform based radon mapping technique is used instead of Fourier transform, inserting a cyclic prefix before transmission which can avoid intersymbol interference. Then the channel can be equalized using one tap equalizer on each subcarrier. Let me discuss about the flow diagram for our process. First, signal has been generated. Input signal information is converted into input data values. Thus, the data value converted into binary pattern and to given the process. The sample data to be given to the process. Then, to plot the sample data signal, the data preprocessing is data mining technique that involves transforming raw data into an understandable format. Real-world data is often incomplete, inconsistent, or lacking in certain behavior or trends and is likely to contain many errors. Data preprocessing is proven method of resolving such issues. Data preprocessing prepares raw data for further processing. Data preprocessing is used database-driven application such as customer relationship management and rule-based applications like neural network. Next, in the OFDM implementation, orthogonal frequency division multiplexing is a method of encoding digital data on multiple carrier frequencies. OFDM has developed into a popular scheme for wideband digital communication, whether wireless or over copper wires, used in applications such as digital television or audio broadcasting, DSL internet access, wireless networks, power line networks, and 4G mobile communication. OFDM is frequency division multiplexing scheme used in multi-carrier modulation method. Large number of closely spaced orthogonal subcarrier channels are used to carry data on several parallel data streams or channels. Each subcarrier is modulated with a conventional modulation scheme. Next, such as quadrature amplitude modulation or phase shift keying at a low sample rate. In maintaining low total data rates similar to conventional signal carrier modulation scheme in the same bandwidth. A fast Fourier transform based in subcarrier OFDM system. Here the transmitter block creates the signal x of t which is transmitted through the channel with pulse shaping. Next, in the ICI power minimization phase, when the system perform in high mobility environment, the OFDM not provide efficient signal where the orthogonality will produce a intercarrier interference. Here we derive the optimum combined weights that minimize the ICI power. Combined signal has been computed by combining the channel frequency response, equivalent ICI term after segment combining, and also the equivalent noise term of the combined signal. In order to find combined signal, the expected variance of the ICI term has been evaluated. Here taken time varying channel as a first order autoregressive model and fully perform the optimization problem to obtain the optimum combining weights which used to minimize the ICI power. The optimization problem solution satisfies the Karush-Tucker condition. In order to produce the optimum solution, this method performed in ICI free region, not consider noise environment. This is the drawback of this method. Next, in the ICI plus noise power minimization. In order to overcome above mentioned disadvantage has been done by this second approach. In this method, we also obtain the optimum combining weights that minimize the ICI power plus noise ratio. Next, this is considered noise environment and also ICI power minimization. Here, combined noise power can be calculated by combining frequency domain noise vector and the phase compensation matrix. Next, finally, the optimum solution has been obtained. This method solves noise environment but not applied for ICI polluted region. ICI process performed only for ICI free region, not taken the ICI polluted region. So that we further proposed the interference plus noise ratio power minimization utilizing entire cyclic prefix. In that ICI polluted region also contains signal information, thus it need to properly employ the signal segments in the ICI polluted region. Here the proposed method that employs the entire CP and obtain the optimum combining weights that minimize the average interference plus noise ratio. Finally, method 3, if the delay is spread is large, performance will be improved by the delay will be large. This method will be performed well compared with ICI power minimization and ICI plus noise power minimization. Let me discuss about the running procedure for our process. Select the OFDM.mpl in the current folder, select the pill and run for executing this process. And this will perform for 3 methods. And this is the input data signal which we have passed to the OFDM channel, and this is the optimum solution for ICI power minimization, and this is the normalized ICI power versus function of Q for ICI power minimization method, and this is the BR versus SNR graph for the ICI power minimization method, and this is the optimum solution which we obtain after performing the ICI power plus noise ratio. And this is the ICI plus noise power minimization for normalized ICI power versus function of Q plot representation. This should be decreased. And this is the BR versus SNR graph for ICI plus noise power minimization. And this is the optimum solution for ICI plus noise power minimization with entire cyclic prefix. And this is the normalized ICI power versus function of Q for ICI plus noise power minimization with entire cyclic prefix. This is the BR versus SNR graph for ICI plus noise power minimization with entire cyclic prefix. This is the received data signal after at the receiver side we received. And this is the final BR versus SNR graph for entire process. Here, optimized OFDM system for high mobility fading channel has been implemented with 3 methods. These methods used to reduce the power minimization of ISA free as well as ISA polluted region. Thank you.